Welcome to Walk About the Galaxy, the relentless astronomy podcast where the science is universal, the opinions are personal, and the guests are planetary. We are strange up and top the astroquarks, also known as Josh Caldwell,
Hannah Sargent,
and Jim Cooney.
Coming to you from the Walkabout studios and other locations near the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Today, we are joined by Dr. Paul Byrne, Associate Professor of Earth and Planetary Sciences at Washington University in St. Louis, also known as the Planetary Guy. Welcome, Paul.
Thanks, Josh. Nice to be here.
Follow us on TikTok, and you can follow Paul on Twitter. At the Planetary Guy.
Yep.
We are also kind of at www.walkaboutthegalaxy.com, where you can see how to order a Walkabout shirt and support STEM education at the same time. Contact us anytime at wtg@ucf.edu, and definitely contact us if you order shirts so we can get it to you as soon as possible. Paul, we start our show off with a stupid question that I make up for Jim and Hannah called a stumper. And it's a stumper because it's a stupid question. And today's stumper is orbiter or probe. And we'll start with Jim.
Probe.
He's stumped.
It's so that was so broad. I don't know.
That allows you to bring whatever you want to the question.
Yeah. Well, I want to go down. I want to go down to the surface. I mean, the Cassini orbiter was great. The Huygens probe was really cool, and I understand that Cassini lasted many more years than Huygens did. But I want to go down to the surface. Probe all the way.
So you're probe, and the Cassini-Huygens mission is it captures the essence somewhat of that question. Hannah, what about you?
Probe all the way.
Really?
Yeah, because with the limited amount of funds, yes, you can get a lot of information with orbiters, but I just like the tactile, hands-on samples and in situ experiments.
In situ versus remote sensing. Paul, how about you?
Yeah, I'm going to go probe. Initially, I was like orbiter because you get this whole grand view of this world, whatever it is you're talking about. But there's something kind of captivating in the image we have from Huygens, or those few images we have from the Venera landers that touched down the surface of Venus. So yeah, I'd love to know what it looks like to see the sun come up on Mercury. So I want to go probe.
Okay, it's unanimous.
Unanimous. All right.
Surprised me. I'm a remote sensing type.
Oh, really?
So, well, yeah. But that's what's been paying the bills all these years for me. It's remote sensing, not in situ. But I totally get it. What if I told you that it wasn't an object with a surface? So, like Galileo probe versus, instead of like a Huygens probe.
Still probe. Got to go down in there. Got to see what's there.
Really?
Yeah.
Okay.
You tell students you dove down into the Jupiter, the clouds of Jupiter or something. That's just cooler than sitting there in orbiter. I understand you might learn less in a short time, but got to go in. Go in.
Got to go in.
There's something very dramatic about diving to its end into the center of a planet. Is just pretty cool.
Yeah. I will point out that although it really didn't really behave as one, Cassini at the end of its mission did dive in.
That's true. It's part of Saturn now.
Yes.
Resting in the atmosphere.
You're going to make me cry, Paul.
I know. I would say then I'm going to keep my answer. If this world doesn't have a surface, I'm going to keep my answer to probe. But the caveat is it has to have a camera because I want to know what it looks like in the cloud layers.
Yeah.
Until it dies.
I definitely am with you on that. Like if the Galileo probe had cameras and we could have really seen some of those pictures and maybe seen Carl Sagan's floating cloud sharks cruising around in there,
yes.
Then definitely that would have been.
I thought you were just going to leave it at Carl Sagan. Just see Carl Sagan.
Maybe that's where it is.
Maybe. Well, today we'll talk about eggshell planets, iron planets, and the relentless growth of black holes. But first, this episode of Walk About the Galaxy is brought to you by Standard Deviation. Is the boss breathing down your neck about that report deadline? Is your professor complaining about that homework not being exactly right? Does your significant other give you a hard time about not making the bed the right way? Then maybe it's time you tried Standard Deviation. With Standard Deviation, there's no expectation for your work to be perfect or even at the expected value. Give yourself a little margin for error and a little time to enjoy the little things in life with standard deviation. If you want perfection, stick to a bit replicable computer simulation. For the real world, enjoy the flexibility of standard deviation. Standard deviation, the best a man can get.
Gillette.
It is Gillette.
Oh, yeah.
Anyway. Space news. There's a suborbital launch of the Blue Origin New Shepard coming up in a couple of days. It'll be their first with 6 passengers on board. 2 guests and 4 paying passengers. The 2 guests are Alan Shepard's daughter and former football star and current TV personality Michael Strahan.
That dude is everywhere.
Michael Strahan?
Yeah. He still does NFL broadcast stuff. Plus he's on the morning show, he's on everything.
Well, now he's going to space.
Going to space.
I planned this whole thing, my whole career in life with a goal of going to space. I planned it all wrong.
Yeah, you should have gone to football first. Yeah.
I don't know, something. There are all sorts of other careers that seem to be more likely to get there. Paul, do you have aspirations?
I would love to go to space because I'd like to know what the rocket launch feels like. I have absolutely no interest in going to Mars. None. I've done long duration field excursions, like geology field trips where we go on ships and we sail through the ocean for weeks at a time. I have no interest in being in a spaceship for 6 or 9 months with nothing to do except try and stop gravity from eating my bones.
Right.
But I would love to go. I'd go to the space station, no problem. Yep. Yeah. I want to feel what the rocket launch is like. I'd come back pretty quickly. But I want to say, if I go into space, and this is in no way a slight to Blue Origin or Virgin Galactic, I want to go into orbit.
Right.
So we're clear.
Sure. Okay. You want to go into orbit, but
you would take a
suborbital hop, I'm guessing.
Yeah, in the way I'd probably take a free plane ticket too, yeah. That doesn't mean that I'm gagging for it though. But certainly, yes, if I had the opportunity to go into space on someone else's dime to the space station, or by the time that likely happens, a space station, I'd definitely take it.
Okay, what's your maximum duration based on your experience on ships? Like how long before the space station you're like, get me out of here?
Yeah, and I try and open the door. A couple of weeks probably. I go to the moon.
Okay.
I'd happily go to the moon.
But same question then. If you're on the moon, assume that maybe
a couple of
something.
Weeks. I'm going up there for a few weeks. I'm going to I don't know what I'm doing up there. Come back. Yeah, go to the gift shop. That kind of stuff.
It's going to get old, changing to go outside and everything.
I wouldn't go outside much. I go out a couple of times. I get the selfie beside the lunar module, that kind of thing. But it'd be a sightseeing trip. Pretty much. Yeah.
Sure. Okay. Maybe they have an excursion you can take on a rover.
Yeah, they've kind of a velvet rope thing you can walk out to and back.
Well, one of the things you might see on a sightseeing trip on the moon, I guess, is moon rocks. So I hear they've discovered some more of those on the moon. Hannah, you were
just moon rocks everywhere. Let's just agree that things in the distance in blurry images are moon rocks. That's it. So yeah, they've got this U2 rover, which is on. It's part of the Chang'e 4 mission, I believe, on the far side of the moon. And one of the images, they've seen a blocky, grainy image of something in the distance. So the rover's going to go explore, and now everyone is turning into a conspiracy theorist, talking about these alien structures on the far side of the moon. And the far side of the moon carries with it these conspiracy theories anyway, because of all of the misconceptions about dark side and whatnot.
Far side, right.
But yeah, there are blocky boulders, big blocky boulders all over the moon. It's nothing special. Let's not get ahead of ourselves.
What if it is? What if it is?
But then wait until we meet said alien or see said structure before we start losing our minds.
Right.
It's always based on sort of the blurriest photos though, right? Like when we get close, if this thing is some sort of cube, great. That's going to be really interesting. I mean, it won't be. It'll be a rock. But it's always the blurriest, poorest quality images that... I posted a picture from the Jezero crater yesterday. Cool photo taken on Sunday with the little Ingenuity copter kind of just to the very kind of middle lower bit of the picture. I challenge people to go take a look at it. People did. But more than a few identified what really does look like a skull embedded in the sand. It's not,
yeah.
And if you can zoom in and blow it up, it does kind of look like a skull, and I didn't have time to engage folks on yesterday, but I'm like, okay, let's say it's a skull. Now you got to explain not just how it got there, but the ecosystem, this thing that's supported it. And suddenly it gets very, very hard quickly to make sense of being anything other than a stone. So I'm completely with you, Hannah. Yes, it's an interesting block, but it's like I'm reminded of the face on Mars. Right. It's so not a face.
I know. I remember, I'm old enough to remember when we got the first good images of the face on Mars, and all of a sudden the face on Mars looked absolutely nothing at all like a face because those first images were just so blurry, so low res. Well, on the rocket launch thing, I've got, since we're coming up on the end of the year, we're just one of our last episodes of 2021. And speaking of going to Mars and the moon, SpaceX's Starship stainless steel beast is getting prepped for its first orbital test flights. Elon Musk has suggested that they may do as many as a dozen flights, orbital test flights, or maybe not all test flights, of that vehicle in 2022. So our end of the year listener challenge is to predict how many orbital flight attempts, at least, meaning the engines were ignited. Now I'll take it, it counts if it goes up and blows up before it makes it to orbit, but how many launches with the intention of getting a Starship to orbit will occur in the year 2022? Submit your guesses to wtg@ucf.edu by January 10th, 2022. Winners will get a shirt, as Hannah's modeling for us on this episode, and a chance to participate in a walkabout episode. So that's our space news. So on the planetary front, Paul, we're happy to have you here because you have a paper out recently that captured some attention about exoplanets, which is one of our favorite topics. Tell us about your work.
Sure. Okay. So we had this paper where we describe a new class of exoplanet called what we call eggshell planets. Now, I'll freely admit we used a term like that because we knew it would have traction and it would get people interested, right? I should say, and this may become apparent as I go, originally we had called these things toffee planets, but I'll describe why we
toffee like the candy?
Well, so yeah, exactly. But it turns out, right, so most of the people on this paper, including myself, who wrote this, are from the British Isles, from the UK or Ireland, where toffee doesn't necessarily mean what it might mean to people over in the US. And really what we're concentrating on, the whole point of the paper is how thick the brittle layer is on a planet. Almost all rocky or icy worlds have this brittle layer. We're interested in what makes it thick or thin. And I'll describe it more in a moment. But
first, I want to understand what the difference is between toffee over here and over there.
Well, it turns out that not everybody universally sees toffee. We wanted to convey it. So let me back up for a second and say, rock can do one of two things, and so can ice. It can break in a brittle way, or it can flow in a ductile way. So think of a Mars bar or a Milky Way, I think they're called here, where you've got a chocolate layer that will snap if it's cold, but the caramel layer will kind of ooze, right? So the same kind of rock under different conditions can exhibit both of those behaviors. And what we want to know is what scenarios lead to a world having a very thin or even no chocolate layer at all.
No chocolate.
To some people, toffee means it breaks. And others, toffee means it flows. And when I ran a Twitter poll last year, and it turns out that it was almost exactly 50-50 to what people thought what that word meant. Yeah. So what we found was, in terms of science communication, it actually wasn't helpful at all to use the word toffee because not everybody knew what it meant in the way we meant it. So ultimately we settled on eggshell planet because the focus of the paper is basically saying that there is somewhere out there in the cosmos a type of world where the brittle layer is either exceedingly thin, eggshell, or perhaps even absent altogether. That's the crux of the paper.
So, yeah, I would for the record, I don't know anything about toffee, but I would have thought of it as viscous, flowy stuff.
As I see it.
Yeah, me as
That's
well.
what I thought too, but
Fractured.
not according to our Twitter poll.
Interesting.
So we were like, okay, we got to change this then.
So yeah, we do an experiment. I mean, your Silly Putty is a great demo tool in class for some of this behavior having to do with the strain rate that you apply to something. So you can take Silly Putty and it flows beautifully, and then you can put it on a hammer and smack it and it shatters.
Right.
And so is that the same phenomena that you're describing here?
Yep, that's exactly it. So it turns out that, and this is something that, because I teach this, and I find every year students struggle to get their head around this because it's not intuitive. But yeah, rock is a viscoelastic or viscoplastic material. And what we know on the surface and what we're familiar with is that almost under every circumstance, rock will behave in a way that if you apply a stress, the rock will break, it will fracture. And that's what you see if you ever drive through a road cut, or even if you look at the blacktop on a road, and you can see how when it cracks because of freeze thaw action, it's got cracks in it. Like, that's the standard thing rock does, and you can see that on the surfaces of Mars and Mercury and the Moon and icy worlds too, where functionally the ice behaves in the same way as rock does. You see, it's got cracks, it's got all the same kind of features we recognize in the rocky worlds, and we can use the same approaches we have to make sense of them. We also know that if you increase the pressure and or temperature of rock and of ice, you get a different kind of behavior. You get this viscoplastic behavior where exactly that. If you have what we call a high strain rate, so you are deforming it quickly, think the hammer and the Silly Putty, it will brittly break, it will fracture. But if you apply that stress really slowly, a low strain rate, that rock will ooze. And that's what basically helps the mantle convect and ultimately drive plate tectonics on Earth, for example. We've known of this behavior for well over 100 years because we have the ability to take a standard common or garden rock and we can do things to it in the lab that will either make it fracture if we deform it quickly or make it flow really slowly if we deform it really slowly.
And so, even in like road cuts, maybe I'm inventing memories, but don't we sometimes even see sort of bent strata?
You see, this is where it's way more complicated than I'm trying to make. I'm trying to skip over all the nuanced detail because it turns out that the answer is both yes and no to your question. This is really, so much like how not everybody agrees that the word toffee means the same thing. Sometimes we use the word ductile to describe this kind of flowing behavior, but sometimes ductile doesn't mean the same to everyone. So what you're describing is what we call a fold, right? Where the rock looks like it's folded over. Right. And it turns out that if you look at that on the scale of, say, your road cut, or let's say you're doing field work in a valley and you look across the valley, you see a big fold. Some folds on Earth are huge. We'd call that ductile deformation. But it turns out it only looks like it's kind of flowing because if you get up close to it, it's just riddled with fractures. So
I see.
Sometimes we call that micro deformation. I'm going to try and skip over that because I spent a whole class on that with my students and they still look blank-eyed at the end of it. But suffice to say, the deformation I'm describing is true toffee-like, which I think we can all agree on, where rock is kind of flowing. That tends to happen tens of or more kilometers under the ground on Earth. We never see it operate because we're dead if we were subject to those conditions. And sometimes we can see evidence of it if that rock somehow later gets thrust up onto the surface, and we can see it. So, for example, if you've got a countertop that has kind of swirls in it that almost looks kind of like swirly ripple ice cream, for example. That's what the rock is doing. And then, by the time it gets up to where we are, it's cold. And that's why you can cut it and you can make a countertop out of it, but you'll still preserve that old structure. But that's what much of the inside of Earth looks like. Now, what we know on Earth is that there is a change in behavior from where the rock will snap and brittly fail to where it's ductilely flowing. And that change is what's called the brittle ductile transition. It's literally the transition from brittle to ductile failure. We've known about this for decades since we've had seismic information. We know where this brittle ductile transition zone is. And what we know as well from lab work we've done on Earth and from a bunch of other stuff, including seismics, is we have a pretty good idea of what governs that transition depth. And if you imagine the depth really as a measure of how thick your brittle layer, think of the chocolate layer on your candy bar.
I'm thinking of it.
We have a rough idea. It tastes good, right?
Milky Way.
Nice, rich chocolate, exactly right. By the way, Milky Way here is a Mars bar at home. That confused me for a while as well.
Thanks for clarifying.
Because I was like, I'm going to buy a Mars bar, and it wasn't. It was what we call, I can't remember what it was, something else. So
like Snickers or something?
Haven't standardized them either.
Yeah, Mars bars here I think they have nuts in them or something.
Yeah, Snickers.
I don't eat them.
Something like that, gross. Yeah, but so what in the US is called a Milky Way, fittingly enough, is what we call a Mars bar.
Yeah.
So we want to know how thick this chocolate layer is. That layer where the rock will snap.
Paul, is that it, on Earth? Am I correct? Do I remember correctly that includes our crust and the upper part of the mantle? We call this.
I'm intentionally skipping over that, but you are correct.
I'm just making sure that I know where.
No, you absolutely right.
Okay.
So this is another thing that really confuses people. And by the way, like full on planetary geophysicists are constantly confusing me in the way. So we have, on the one hand, we have the lithosphere, and then we have what's called the asthenosphere, which is that deeper part of Earth that's moving. We think it's hydrated, it's able to move and essentially ultimately drive plate tectonics or help drive it. Depending on who you talk to, the lithosphere is the brittle layer. The lithosphere, in fact, is not. The lithosphere has both a brittle and a ductile layer. And then separately, you have crust and mantle. And they are not the same. You can't equate the two easily.
Well, I knew that, so I thought I was with you until you said the lithosphere includes ductile stuff as well.
Right.
So I thought litho means rock, and that was the brittle part. And that's sort of what defines the lithosphere is its behavior. So what is the definition of the bottom of the lithosphere then?
The bottom of the lithosphere is where we see a change in seismic velocity because you see a material change in the rock mechanically. But the lithosphere, often people use the word lithosphere to mean just the brittle layer. But if you look at our strength models and where we compare that to, say, our seismic data, there is a brittle and a ductile part of the lithosphere. And so in the paper, we're clear to say we're talking about the brittle lithosphere because it's not straightforward. And in fact, depending on where you are on Earth and probably other worlds too, you can even have two brittle ductile transitions. You can have a brittle part of the lithosphere and a ductile part of the lithosphere. Or actually, more specifically, you can have a brittle ductile transition in the crust and one in the mantle, but it's not straightforward and it's not the same everywhere. So no one has ever standardized these words in the way that they should be. So in the paper, you'll see we always write the word brittle lithosphere.
We'll have you back on another episode to talk about the word planet sometime.
So I wrote a thing, by the way, about 8 weeks ago about why Pluto should be considered a planet. So I would love to come back and talk about what doesn't make a planet.
Well, no, we've beat that dead horse so many times.
I'm going to keep beating it. I've got a big stick for it anyway.
But so now you found some exoplanets with very thin or absent brittle.
Right. So for the remainder of this conversation, I'm going to refer to it as the brittle layer because I think that's just going to be, forget all the fancy terminology, right? This brittle layer is really important because it controls a lot about a planet. It's not that it controls. It's more like a manifestation of the properties of that planet. But for example, take Mercury or Mars or the Moon. The brittle layer on those worlds is tens to hundreds of kilometers thick. And one of the consequences of that is that you might have, even say for Mars, you could have mantle convection on Mars today. The mantle is moving slowly because it's still hot. And the bottom of the mantle is hotter than the top part of the mantle, so it's going to convect. But if your brittle layer is thick, it doesn't really matter how kind of vigor you have in the mantle. It's not going to really affect the surface at all. And it's going to have all kinds of implications for how you get heat out. And the dominant way you get heat out is through volcanism if you don't have tectonic plates. Take Earth. Earth has like that kind of sweet spot. The brittle layer, which is the lithosphere, so it's the plate, which is the crust in the uppermost mantle. That brittle layer is thin enough that the mantle can deform it and break it, but it's thick enough that the plates can pull themselves down and sustain plate tectonics, right?
Instead of like disintegrating or melting
pretty much, right? And this is kind of more kind of thing. What's the end member? So Venus, I had a paper that came out earlier this year where we were describing stuff on Venus moving around in a way that we described as looking like pack ice. And what we think is happening on some parts of Venus, in the Venus lowlands. In fact, actually, in our most recent paper, we describe how the Venus lowlands might be a good counterpart to a so-called eggshell planet. The lowlands of Venus is very high-standing highlands as well, and they're probably very thick. The brittle layer is very thick there. But in the lowlands, we think the brittle layer is very thin. And there's a few reasons we have for thinking that. But what we think is happening there is stuff can move, it's thin enough that the stuff underneath can affect it, the mantle moving can actually deform it. But the layers themselves, or that brittle layer, is too thin for it to subduct. One layer can't really get below another, or one part of that same layer can't go below another. So instead of diving down, it just sort of crumples. Right? So like imagine trying to subduct two pieces of tissue paper, right? It's not thick enough. So the thickness of this brittle layer really controls indirectly whether or not, for example, you can have plate tectonics. Plate tectonics is the dominant method for cooling Earth, because those cold plates that have radiated their heat, well, have conducted the heat into the oceans and then into space, those plates, when they dive down, are extremely cold relative to the surrounding mantle, and therefore the mantle can dump its heat into them again before they get recycled back up. It's also an extremely efficient mechanism of drawing carbon down through the carbon silicate cycle and therefore regulating Earth's temperature, which is why Earth's atmospheric composition is dominantly nitrogen and organically derived oxygen instead of CO2, like, say, Mercury or, say, Venus or Mars. So plate tectonics are really important. Plus, plate tectonics governs not volumetrically all, but most of where the volcanic and tectonic activity on Earth is. It's around the edges of the plates. So plate tectonics shapes, and this is totally separate to the parallel conversation of plate tectonics' role in planetary habitability, because we don't know. I'm not sure how definitively we know that one way or another. But if you don't have plate tectonics, which are a large world, that has implications for how you get heat out, where you get heat out, what chemical reactions you can have. Can you sequester certain chemicals into your interior again? Even what the surface looks like. Can you have large mountains? Can you have big orogenic mountain belts where two plates collide and produce? And we're suggesting that for these so-called eggshell planets, they don't have any of this. Even if they would otherwise be big enough to sustain plate tectonics, they can't, because the brittle layer is too thin.
So how did you determine that you've seen eggshell planets? What's the?
Oh, it's all lies. We haven't seen them, but
it's modeling.
It's modeling. It's all modeling, and all models are wrong. Some are useful. So what we've done is this: we have a fairly good understanding of how rocks behave from lab work, decades and decades of lab work, and observations and seismic data. We have a fairly good understanding. I mean, that's probably not right. We have a good understanding. There's a lot we don't know, and particularly the ductile deformation, where the rock is deformed over very, very, very low strain rates, i.e. very, very slowly. It's extremely difficult to model that in the lab. So actually, we don't really have a great handle. And often, too, when we estimate how rocks behave, we characterize one mineral. We say, this is the law we think governs how a rock made of this one mineral behaves. And of course, the rocks down there are not monomineralic. They're made of one. So it's way more complex. But again, they're models. They're a starting point. So what we did in the paper, in fact, we weren't setting out to do the eggshell thing. All we wanted to do with the paper, we were like, okay, look at the solar system, look at the rocky worlds and even icy worlds, although we focus for the paper on rocky worlds. This is the range of masses they have, of surface gravitational accelerations they have, of surface temperatures they have, of estimates for how much heat comes out of the interior. We call that heat flux they have. Now, what would it look like, or what would happen if we extended the ranges of all those parameters? Right? Imagine the solar system was only 1 billion years old, or the planets were born with more radioactive elements per volume than they were in real life, or the worlds are larger, or they're closer or farther from their star. We changed a whole pile of parameters, and we ran 100,000 models to try and estimate, broadly speaking, what kinds of combinations do you get and how do they interact that end up predicting where that brittle ductile transition is, where that change in behavior is, ultimately how thick that brittle layer is.
So can you find, looking at these different variables for, say, a habitable zone, is there a link? Can you predict generally how thick the lithosphere is for these habitable zones, and I guess what the tectonic activity you'll expect? Will it always be similar to Earth?
So the terrific answer is no, we cannot predict that at all. And the reason we can't is because Venus has told us that we cannot simply assume, which is personally one of the 8 reasons why I hate the phrase habitable zone, because it's become a short, because originally, right, when they wrote about it in the 80s and 90s, the idea was, where could you move Earth, modern Earth, radially to a world and it retain liquid water? And that gets dropped in favor of a shorthand that suggests that if you're in the habitable zone, you can have liquid water, as if we were to tractor beam Mercury out to 1 AU, it suddenly becomes habitable, right? So we lose a lot.
It would be cool, though. Even if
hang on. If we're going to tractor anything, I'm going to tractor Mercury into Mars, because that's one of the most effective ways we get Mars sample return. Because some of the debris cloud surely.
I thought you just wanted to get rid of Mars.
You're gonna take.
It's also a benefit. I'm just saying, right? It's also a benefit. Yeah.
You're going to take a planetary tractor beam and the only thing you're going to do with it is smash Mercury into Mars so that you can get some free meteorites from Mars landing.
No, that's not the only thing I'm going to do, because I'm going to then tractor the rest of them into. I'm probably going to throw them all into Jupiter, actually.
Oh well, okay.
I'm not going to stop
playing around with it.
If I have this ability.
Yeah.
But until and if I get that ability, yeah. So basically, what we've learned from Venus is that Venus orbits about 70% as far from the sun as we do. All things being equal, which they are not, solely on the basis of sunlight, incident solar radiation, Venus ought not to be very much hotter than Earth. And in fact, this was the kind of prevailing view until like even as late as the 50s and 60s, that there might have been, people wrote about these lush rainforests in Venus. It's a little warmer than Earth, right? And then Mariner 2 turns up in 62 and goes, oh my God, the surface is like big. Now, people often say it's the temperature hot enough to melt lead. I don't know what that temperature is, and I have no intuition for that, but I know that it's self-cleaning oven temperature, and when your oven is in self-cleaning mode, you don't go near it, so it's hot. And what that basically and so in our study, and Hannah, to your question, unfortunately, we cannot just say purely on the basis of distance to the host star that it's likely to have the following. And in our study, what we found was the most important control over anything else to govern the thickness of that layer, thick or thin, is surface temperature. And what we've said in the paper is we are completely agnostic as to why that temperature is high or low. And in the case of an eggshell planet, it needs to be high. It can be high because it's close to its parent star, and or because it's say in the case of Venus, it's undergone a runaway greenhouse effect. It can be a combination or either or. Now, when I say hot or high temperature, I don't mean there's a world, for example, we know called 55 Cancri E, and we suspect strongly that its surface is in fact molten. It is so close to its parent star that the surface temperature is like 1800 Celsius. We're not talking about rock that is molten. We're still talking about solid rock. But it could be that. And what we also found is another thing that controls, we know this, one of the things that controls rock brittle or ductile behavior is pressure. And one of the ways you can have high pressure relatively shallow down is a large planet with a high surface gravitational acceleration. So you can imagine a scenario that the optimum eggshell world is a large world bigger than Earth, a rocky world like a super Earth, that has a high surface temperature, a few hundred degrees, either because it has a runaway greenhouse effect or because it's closer to its star. That is the kind of the classic example of an eggshell world. Now, in our study, we considered there's only about 20 exoplanet super Earths for which mass and radius are known. And we need both of those numbers, not just to estimate that they're rocky in the first instance, but to be able to plot them. And because we can then make an estimate, assuming some density for what the surface gravity is. Again, we've got error bars, but we can start to estimate this.
Well, so yeah. One of the things, also that we love to talk about on the show is life, and so habitable zone types of conversations come up frequently. And one of the things I was fascinated by when I was just doing some sort of amateur education of how evolution works is the importance of geological activity,
right?
In terms of moving things around and separating habitats so that you can have proliferation of different types of species. So you don't really want. We're not on an eggshell planet here on Earth, and that's a good thing. And so, it's very, very interesting. And I'm sure that we've been talking about JWST coming up with its launch in just a couple of weeks now.
Yep.
We'll be getting more amazing information about exoplanets. So very cool. I'm Go ahead, Jim.
Oh, I was just going to say the cool takeaway. I mean, details aside, one of the cool takeaways is every time we talk about exoplanets, like every time you teach it in a class, in an intro astronomy class, it's just we know there's just a greater and greater variety of possible ways to make exoplanets, and it's just
right.
Our solar system is not the only way to do it. The handful of kinds of planets that we have. I mean, it's nice that we can categorize our planets into a few categories, but it's just not like that. And there's such a crazy variety of things out there that we're discovering and finding are realizable. It's kind of awesome.
And that was one of the core points of the paper, absent the actual eggshell planet side of things, is what happens if you take worlds and you just change the dials beyond what you see in the solar system. Yeah. And then we make some predictions. And Josh, you talked about James Webb. We predict that these eggshell planets, for example, should not have high standing mountains or topography. Webb won't do this, but perhaps the generation of telescope after that might actually be able to search for topography on these exoworlds. We predict that the atmosphere probably will look more like Venus than Earth because the difficulty in drawing the carbon down.
Right.
If we find in the atmosphere that it's CO2, that isn't a definitive plus for us. But if we find a large rocky world we predict as an exoplanet, an eggshell world, and it's got a nitrogen and oxygen-rich world, then that suggests that we were wrong. We've got to go back and refine the ideas. So some of this is testable, as opposed to some geoscience meets exoplanet stuff where you can pontificate, and it'll be 300 years before someone can prove it wrong. There are some testable things in the paper.
Well, speaking of testable science, our next topic is going to deal with a test in the realm of astrophysics. And as a transition to that, for our trivia today, we've got some black hole related trivia. And Jim, you may recall that in the last episode, Hannah kind of mopped the floor with you on identifying the authors of some famous quotations, famous scientific quotations. She got 2 out of 3 to your, and you came up with a goose egg.
Yeah.
So I'm going to give you a chance at redemption this time with more quotations, all about black holes.
Oh boy!
So it's match the scientist to the quotation.
I need these scientists written down though, because I can't remember a list of 3 names. I really struggled last week.
Okay. Actually, I've got quite a lengthy list here this time. But in any event, you'll recognize most, if not all, of the names, I'm sure. So what I'm going to do, Paul, just is I'm going to read the quotes and the choices, but don't blurt out your answer if you know it, because we're going to come back to that after Jim tells us about the black hole area theorem. So here are your quotes. The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time. That's one. Second one is, God not only plays dice, but also sometimes throws them where they cannot be seen. That's 2. 3, black holes are where God divided by 0. And 4 is, when I was 4, I wrote a song about falling into a black hole.
That's a quote.
That's a quote. And here are your choices. Albert Einstein, Stephen Hawking, Roger Penrose, John Wheeler, Subramanian Chandrasekhar, Neil deGrasse Tyson, Billie Eilish, and Adele.
I see.
So we'll come back.
What is Billie Eilish doing in an astronomy and planetary podcast?
She may have said one of these things about black holes.
Okay.
Or not. Could be a distractor, Actually, speaking of Stephen Hawking, one of the choices there, one of his landmark papers in the 70s had this prediction that I guess was not self-evident about black holes sort of inexorably growing.
Yeah, back in the 70s, Stephen Hawking was doing some crazy things with kind of equating the physics of black holes with thermodynamics, right? So we have all these great ideas about thermodynamics in regular mechanical systems and even quantum mechanical systems. We have the great rule like entropy in the universe or entropy in any isolated system has to always either stay the same or increase, right? This is one of our fundamental laws of thermodynamics. But there's always been a great question about like what happens in a black hole, right? So if I take some cloud of hot gas, there's a lot of entropy there, right? Because there's a lot of random motion of all these things. What if I throw that into a black hole, right? One of the fundamental things about a black hole is this beautiful theorem called the No Hair Theorem, right? Which we've mentioned a few times in the thing, which is that like there's no information in a black hole other than what its mass is, what its electric charge is, and what its angular momentum is, or what its spin is. Those 3 pieces of information are it. And so it seems like you've lost a huge amount of entropy by chucking this hot pile of gas into a black hole, and all of a sudden things are much more simple. So disorder seems to have gone away rather than kept itself. And so what ended up eventually happening is Hawking and others around that time kind of ended up equating, and not just like arbitrarily for good reason, the area of the event horizon of a black hole to entropy. And those don't seem like concepts that are particularly related, but they maybe are if you think about it. Like, I mean, if you were a distant observer watching this pile of gas fall into the black hole, one of the awesome things, of course, about black holes, as we saw in the epic film Interstellar, was that yeah, everybody.
Yeah.
Yeah. Well, I assume you liked this movie Interstellar, or am I wrong?
Yeah, I did. It kind of got weird at the end.
It did. I agree. The end got weird, and the power of love.
Visually, it was terrific.
Yeah. But anyway, we're just making sure that Josh here is in the minority of not actually liking the movie. So, in any event, one of the cool things we saw, of course, is that for a distant observer, time slows down for things that are getting close to the black hole, right? So the closer that object gets to the black hole, the slower its time is running. And the event horizon of a black hole would be that kind of that point where time would slow all the way down. So that is, you could wait an infinite amount of time. You're never actually going to see that stuff fall into the black hole, just kind of settle into a very, very, very close to it if you wait a very long amount of time. And so what that kind of means to a distant observer is the entropy doesn't actually go away. It just kind of spreads, or it's not the entropy itself spreads, but the stuff is kind of spread around the area, the surface area of the event horizon of the black hole. And so you can think of the amount of entropy in a black hole as being characterized by how large its event horizon is. Or when I say how large, I specifically mean its surface area. So not the volume inside, not its radius, but its surface area specifically. And so if you then kind of equate the second law of thermodynamics, which says entropy has to stay the same or increase, and you apply that to the surface area of black holes, then you can say the surface area of a black hole, or a system of black holes, if you have a bunch of black holes hanging around, interacting with each other, the total surface area of that system always has to either stay the same or grow. And so that's the kind of second law of black hole thermodynamics. And that's a tough one to test, it turns out, because you don't get to go and play around with black holes in your laboratory and then check what their surface areas are. But we recently have been able to test this, at least in a kind of crude way, with looking at LIGO results, right? We've seen all this awesome information about the collisions of black holes in LIGO, and so we can kind of test whether the growth of the total surface area of black holes, basically LIGO has seen the very first spotting that LIGO made was a pair of black holes colliding together to make one big black hole, and it's seen that numerous times since then. But there's a paper just out analyzing that very first collision, which is the big famous one, where they looked at what the surface areas of the original black holes were compared to the surface area of the final black hole, and we're not measuring these directly. It's amazing to me because really all you're seeing is like these wiggles and how far apart these two test mirrors are from apart from another. But by analyzing those wiggles carefully enough, you can kind of get a lot of information about what went into the collision and what came out of the collision. And it turns out that Hawking's prediction was validated at least to 2 sigma, 2 standard deviations. It's not that's not really our
sponsors.
It's sort of at the planetary science standard for. Yeah. That's a good result, and not the particle physics standard.
Right. That means we're 95, 97, something like that % confident that that it was that the second law was satisfied. But
in other words, that the new bigger black hole has a larger surface area than the sum of the surface areas of the 2 black holes that went into forming it.
Correct.
And here, surface area of black hole, I'm talking about the surface area of the event horizon.
That's right.
And that's not something that would be, necessarily intuitively obvious, right? Because, for example, one thing that happens is, I think in this particular collision, 3 solar masses of matter was transformed into energy.
That's right. So the total mass of the system, the total mass of the black hole system decreases, right? Because you take away all that energy because of the gravitational waves. And so you might think, if I lose all that energy, I've lost total mass. And of course, the radius of a black hole, the radius of the event horizon, is related to the mass, right? So you take mass away, that shrinks it. But this law says you can never shrink it enough that the area would be smaller than the areas to begin with. And it seems like it isn't, which at least is a check mark in the favor of Stephen Hawking and his.
If I take 2 wads of silly putty and I smash them together, the area is going to be smaller than the areas of the 2 things that went into it.
So does that mean it's less dense?
Well, density is a funny thing for black holes, right? The density is, in some sense, infinite, right? I mean, because the mass is not obviously spread out throughout the interior of the event horizon. The mass is all in the middle at one spot, or not exactly one spot, if you believe in quantum physics, which we all do. And so we don't know. Again, all of this needs to be taken with a little bit of grain of salt, right? Because all of this is kind of Stephen Hawking's, and not just Stephen Hawking, but all of his collaborators and stuff. Their attempts to kind of put quantum physics into relativity, which we don't have a formal theory for yet. But these arguments based on things like entropy are pretty strong arguments about not what exactly it must be like, but what kind of it must be, what must kind of be like. And it's fun that just based on these like entropy arguments, you can make this area argument, and it seems to be working out. So that's pretty
so far, at least with the first testable prediction.
That's right.
That's kind of cool.
It's better than passing is better than failing. That's what I've heard. That's what my students tell me.
And we're bound to get more and better data to up that 95% to 99%.
That's right. That's right. Yeah, this was just an analysis of that very first LIGO collision that we saw. We of course have a few dozen LIGO interactions since then, and the more now we have Virgo in line, and there's a few more gravitational observatories that are being worked on, and so the higher, the quality of our data, the more we're going to be able to test this, and we'll see. We'll see if Stephen Hawking deserves that Nobel Prize. Of course, he can't get it because obviously we don't give Nobel Prizes posthumously.
Yeah, but it also goes to show, just it took this long to publish that from when the data were acquired, 2015. That it really takes a long time to reduce those data and actually make sense of those almost imperceptible changes that you can detect.
Yeah. It really is remarkable when you saw those. It was. At the time, they showed those wiggles, kind of show and to me, even being kind of adjacent to this field, I mean, I'm shocked at how much information they're actually getting out of what looked like a few simple wiggles, right? But there's actually a huge amount of data there, of course.
I feel the exact same way about exoplanet detections. You see a bunch of wiggles, and someone can tell you where the other planets are. I'm with you. Yeah, as a planetary geologist, I like images. I can count at craters. That's easy.
Right.
Well, it's because those wiggles come on a foundation of an understanding of how the universe works, and the universe made those wiggles according to certain rules. So that helps out a lot. Well, speaking to your question, Hannah, about the density of the black hole and the singularity at the center, that brings us to one of our quotes in your trivia. So I'll start with that one, actually. Black holes are where God divided by zero. Who said that? Was it Einstein, Hawking, Penrose, Wheeler, Chandrasekhar, Neil deGrasse Tyson, Billie Eilish, or Adele?
Paul gets the guest first because he's the guest.
Well, I thought Hannah was going to go first. I'm much more comfortable if I'm not going first.
Okay, Hannah.
Penrose.
Penrose.
I'm going to be different. I'm going to say Neil deGrasse Tyson.
That was my second choice.
Okay, so Jim's strategy was apparently, I won't get beaten by Hannah because I'll guess.
It's always the same thing that she guesses. I can't look.
That way I have it. At least I will do no worse than a tie. Actually, it was Einstein.
Ah.
Yeah. Let's get this one out of the way. When I was 4, I wrote a song about falling into a black hole. Was it one of 6 scientists I just listed, Billie Eilish, or Adele?
Eilish.
I'll go with Eilish also.
Yeah, me 3.
You're all correct. So I'll leave those 2 off of the remainder. I'll give you Yeah, that neither Adele nor Billie Eilish said either of these next two quotes.
It was great, by the way, that you picked two. Oh wait, never mind. That's not true. I was going to say you picked two from the British Isles, but Billie Eilish is not from there. She's from the U.S. But Adele is. Okay.
The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time.
Hawking.
You know, I was going to say Hawking also. Just so that I don't be a jerk, I'll say Penrose on this one.
I'm going to go back to Neil deGrasse Tyson.
Wow, I'm stumping you guys big time, except for the Billie Eilish one. It's Chandrasekhar.
Oh, my.
Yeah.
We're all tied, though, so that's good.
Your last
so it comes down to this last one, then. All right.
Your last chance. This is it. All or nothing, Jim.
Yep.
God not only plays dice, but also sometimes throws them where they cannot be seen.
It's either Hawking or Tyson. Hawking.
Hannah says Hawking.
That was going to be my guess, too, so I'm going to go with it. I'm sticking with it. Hawking.
I'm going to go with Hawking, too.
Well, you are all correct. It was Stephen Hawking with that quote. Well, while it may have felt like waiting for a big bag of entropy to cross the event horizon, it was just another episode of Walkabout the Galaxy. Write us a review on the back of the U.S. Constitution in the National Archives and get Nicolas Cage to break it out and discover it, and then make a movie about that. Thanks to the Planetary Guy, Dr. Paul Byrne, for joining us. Follow him at the Planetary Guy. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel where you can see most of our episodes, some of our bloopers, and all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter
at walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Production assistance provided by Diego Rodriguez. Thanks again, Paul, for joining us on this episode
My
of Walk
pleasure.
About the Galaxy. A pleasure to have you. Thanks to our listeners in Missouri and around the world. Stay safe. I'm Josh Caldwell.
I'm Hannah Sargent.
And I'm Jim Cooney.
We're the AstroQuarks signing off until the next episode of Walk About the Galaxy. Ta-da!